Alright, hello everyone. So let's begin this section. So if you recall from polar coordinates from 15.4, where x equals cosine theta, y equals r sine theta, and r squared equals x squared plus y squared. Well, in 3 dimensions, there is a coordinate system called cylindrical coordinates, which will be using these equations as well, which will make evaluating triple integrals much easier. Now, in the cylindrical coordinate system, where we have a point P in 3-dimensional space, is represented by the ordered triple of r, theta, and z. So as you can see, r, we would get it from here. Theta, we would obviously get it from here. And well, our z will be our z. Now, to all the visual learners like me, let's, oh, nope, that's not y. That's z, y, and x, right? So our point would be this. This is our point, right? P, which would be in these coordinates. And so this is our angle, theta, our r, which is our radius, and this would be our z. So this is our main graph to be able to understand for this 3-dimensional space or ordered triple that they called it, which we will be using in order to evaluate triple integrals of certain regions. So knowing this and recalling these equations, let's head over to start converting from cylindrical coordinates to rectangular coordinates. So what this is would be called a cylindrical coordinate, right? So r, theta, and z. So let's begin on doing that. Okay, so to convert from cylindrical to rectangular, so cylindrical would mean with the coordination of r, theta, and z. Rectangular is with the coordination of x, y, and z. Okay, so to convert from cylindrical to rectangular, we need to use the equations we previously mentioned, r cosine theta and y r sine theta. Okay, so for example, we have the point 4 pi over 3 and negative 2. So this is our r, this is our theta, and this is our z. So in order to get our x, we just plug in. We plug in our r and our theta. So we get 4 cosine of pi over 3. So our x, this equals 1/2. So 1/2 times 4 is 2. And then our y would be the same. But now instead of not cosine, we do sine pi over 3. And so that would be 2 rad 3. And so our z is just our z. So it's the same value. Z equals negative 2. So our rectangular coordinate would be 2 rad 3 and negative 2. Okay, now if we go the opposite way, if we go from rectangular to cylindrical, so now if we go this way, we would have to use r squared equals x squared plus y squared to get our r, and then tangent theta of y over x. Okay, so for example, we have the point 2 rad 3 to negative 1. So this is our x, our y, and our z. So we would plug in into this one, to r squared equals 2 rad 3 squared plus 2 rad squared. So we would get 16. R squared equals 16, so we have r equals 4. Okay, now to get our theta, our angle, we would just plug it in there, into this equation. So tangent theta of 2 over 2 rad 3, so theta would be the inverse of 1 over rad 3. So our theta equals pi over 6. And well, here our z as well is the same value, z equals negative 1. So our P, our new point in cylindrical coordinates, would be 4 pi over 6 negative 1. So that would be our point. So it's not very hard, it's just plugging in and evaluating from there. Knowing how to do these conversions, let's start with evaluating triple integrals with cylindrical coordinates, which is what we will be mostly doing. So let's say we have a region whose projection D on the x and y plane, which is described in polar coordinates. So let's first do the region. So we have a region, which we're going to call this one a region E. So I'm not a very good drawer, as you can see. I'm going to try my very best. Okay, so we have this region, right? And we're going to call this region E. And so it says that it makes a projection. So makes a projection we're going to make this projection here. So D says it makes this projection D. Alright, so if we think of this and we start plugging in just similar to triple integrals and similar to polar coordinates as well for 15.4, this right here is our theta to, this is our radius of H2 theta, and that's R1 theta. Okay, and so now this, remember, from 15.4 polar coordinates, it was basically this that we were looking at. And now we're doing with this, which is where the triple integral comes from. We're doing 3 different integrals now. We're considering 3 different ones. So now we're considering the height now, the height. So this and the projection that it makes. So for this is our second height. So this is our first. So U equals this. So this is our Z. This is what our Z is going to equal. Okay. So we have this graph. So we're going to say in this region, when we write our limits, the book says this, and I'm going to write it down because that's what the book says. But then I'm going to show you the longer way, the way that I like to write it, much longer, and it's already going to be put into polar coordinates, but that was easier for me to understand it. It was easier for me to plug in the limits, to know better the limits of the region when we do a problem. So let's just write what the book okay, and our U is divided by U2. Okay, so this here is this region. That's what they mean by this. This part is this region, and then this is the projection, I'm sorry, and this is our region, okay? But now, like I said, I like to write it the longer way, already in polar coordinates. So since this is already in polar coordinates, as you can see, then we can just write it down. So remember we previously went through okay, so our theta Z, and so our theta is bounded by that, then our radius bounded by that, and so now our U is going to be the same. Our boundaries for Z is going to be the same, except now we're going to put into polar coordinates. So our X and our Y, remember, our X is R cosine theta, and our Y is R sine theta. Right, and then the same thing here. R cosine theta, R sine theta. Okay, so this is the way I like to write it. It's longer, but when I was first going through this section, this is how I understood it much better. I thought it was much easier. Okay, so understanding the limit for the triple integral of cylindrical coordinates, let's now look at the integral equation. So knowing the triple integral equation for 15.7, so the previous section, which is f of x, y, and z dv. So now our equation for cylindrical coordinates, the book has double integral of region D. So remember, that was the region on the x and y plane. So it was the red region that I had drawn. it was like that, so it was this region, right? So this is the integral of that region. So the double integral of that region and the integral of z. So it would be, and that was the blue region, the one that we drew in 3D here. Okay, so this one here that we're writing right here is the integral of that region. Okay. dz of that, and then dA. Okay, so this is the version that the book had given. If you recall, the one that I said that I really didn't like using. So now if we plug it in, and knowing how to evaluate the double integrals in polar coordinates for 15.4, then we can combine this equation with the double integral in polar coordinates equation, and so we would get, so triple integral dv, and so we would get integral of our theta, integral of our radius, and an integral of our z. But like we did in the longer version, the one that I had mentioned that I like to do, instead of the short one, the one that book gave, then we would do the exact same thing. We're just basically putting that into integral format. So remember how we also plugged in our polar coordinates? And so we're doing the exact same thing here. The exact same thing. And so I thought our function would also be r cosine theta, r sine theta, r dz, dr, d theta. So you see the connections between the limits that we had previously done with the integral. All we did is plugging it into integral section, and we involve now our function. Also recognize that our dv here equals this right here. dv equals r dz, dr, d theta. And just like in 15.4 for polar coordinates, of not forgetting to not forget the r, the same thing here. Do not forget the r, because our r is what's gonna make the integration most of the time much easier. So always remember the r. So just remember that dv equals that, so you must have that. So besides having these limits in your function, you need to remember to have that as well. So this equation will be our guidance in evaluating triple integrals with cylindrical coordinates. So knowing this and hopefully understanding this, we can go on and start examples. Alright, so our first example is this. It says, evaluate the triple integral x squared dv, where E is a solid that lies within the cylinder x squared plus y squared equals 1, above the plane z equals 0, and below the cone z squared equals 4x squared plus y squared. First of all, my biggest advice that I gave you before we start with this example is to always draw a picture first. It will sometimes help you answer the problem, especially if you're a visual learner. So let's start drawing this one. So it says that the solid lies within the cylinder of y squared plus x squared plus y squared equals 1. So if we draw the cylinder, so it's equals 1, right? So then our radius is 1. So our radius, let's say 1 was there. So our radius would be this. It would go basically all around Z. It would go all around Z. And then it says above the plane, Z equals 0. So what that means is that it's everything from here up. So the bottom part is not in place. So we don't consider this bottom part. So the bottom part of the cylinder is out. Okay? So now we only have this part here. The top part. So we only have the top part. And then it says below the cone, Z equals squared 4x squared plus 4y squared. So our cone, that means our radius here is 2. So that cone is this. Okay. So it says that the solid within the cylinder. So that means inside the cylinder. So we want to figure out this region right here. This part here. Okay. So what we do next, what I'd like to do next after doing the picture first, I'd like to do to convert to polar coordinates. So have each part that we have here, whatever it is that we need to convert it to polar coordinates. So our first one is this one here, our cylinder. So x squared plus y squared equals 1. So this, remember from our equation, r squared equals this. So r squared equals 1, which means r equals 1. So right here, we already have a radius. Next is our cone. And so it says z squared equals 4x squared plus 4y squared. Well, this equals r squared, right? So we have 4r squared, which means that z equals 2r. Okay, so look at this, z equals. So this must be part, this somehow, somewhere is going to be part of our z integral. Okay, so now let's put it into our limits. So let's write it down. So our radius is basically from 0 to 1 because it's within the cylinder. We're not considering the cone, we're considering inside the cylinder. So our cylinder has a radius of 1. So our radius is gonna go from 0 to 1. Okay, now our theta, it's going all around. There's nothing telling us that it's only the first octant or only a quarter of it. It's going all around. So that means our theta is going to be 0 to 2 pi. And now our z, so we know right here, from this one right here, that z equals 0. So from z 0 and up, so from z equals 0 to z equals 2r, to the cone, to where the cone limits the cylinder. So our z ranges from 0 to 2 pi r to 2r. So now that we have this, we can now put it into our triple integral. So now our triple integral, we're not going to have enough space to actually do the solving, so I might erase this. But our triple integral is now from 0 to 2 pi, which is our theta, 0 to 1, 0 to r. And so they give us a function here. So this function is what we need to write here. But this is in rectangular coordinates, so we need to change this into polar coordinates. Well, it's x, so x equals r cosine theta. So all we need to do is plug in r cosine theta, which is squared. So we would do, so that would equal r squared cosine theta squared r dz dr d theta. Okay, so this is our integral. So let's start solving it now. So I'm gonna have to erase here. Okay, so let's put it up here. 0 to 2 pi, 0 to 1, 0 to r. So this here, r squared r, is basically r cubed. Cosine squared dz dr d theta. So now that we wrote it there, okay, so let's first now integrate in respect to z. So integrating that, we would get from 0 to pi, 0, 1, we get z r cubed cosine squared, 0 to pi dr d theta. Okay, so then this becomes two r to the 4th power cosine squared dr d theta. So this here, we can separate the integrals to make it easier to evaluate. So we're going to separate 0 to pi. We get here d theta. And so let's do this part. Let's do r here. So from 0 to 1, 2r to the 4th power dr. But this is going to be more work, so let's actually switch. So let's do dr here. So 2r to the 4th dr, 0 to 2 pi cosine squared d theta. So this is basically easy to integrate. This is 1 over 5 r to the 5th power, and so this becomes just 2 over pi. Okay, so that's one of our answers. Our second part is here. So this we can integrate just like that by just that, so we would have to use the half angle formula. So we would do from 0 to 2 pi, this becomes 1/2 1 plus cosine 2 theta d theta. So we would integrate that. We would have theta plus sine to theta from 0 to 2 pi. And so that just becomes 1/2 2 pi minus 0, so we get pi. So therefore now we multiply these two together. So our answer is 2 pi times pi, which is 2 pi over 5. And that's our answer. Okay? All right. Let's go over to our second example. Okay, so our second example is find the volume of the solid that lies within both the cylinder, x squared plus y squared equals 1, and the sphere, x squared plus y squared plus z squared equals 4. So here, let's start with doing the picture first so that we know what we're talking about. So our sphere is equal to 4, so that means our radius is 2. So we draw our radius, like to do it this way. So radius is that. And then here. Okay, it's a bit crooked, but you know, a radius. And then it says that lies within the cylinder and the sphere. So let's now draw our cylinder, and our cylinder is 1. The radius is 1, so our cylinder is gonna go here. So the area, the volume that we have to figure out is the one in here, the one that's in both the cylinder and the sphere. So this part here, okay? So the inside, that's what we have to evaluate. All right, so again, let's now convert to polar coordinates. So we have this one and this one, right? Our cylinder and our sphere. So our cylinder is x squared plus y squared, which this equals r squared equals 1, so then r equals 1. All right, so there we have a radius. Here, now here what we want to do, since we want to change it so that it can be a function of x and y. That means we're gonna have z equals. Because remember, our height is of z, right? That's what our first integral is going to be of. In terms, it's going to be z equals a function of x and y. So we need to change that. So we're going to have z squared equals 4 minus x squared minus y squared. All right? So remember, this is r squared. So 4 minus r squared, we integrate that, z equals 4 minus r squared. Okay, so there is part of our z. So now let's set up our limits. So we know that it's a cylinder, right? And so we know that it's gonna go through, it's gonna revolve around a full circle. So that means it's gonna, our theta, it's gonna be from 0 to 2 pi. Oh, wrong one. So r theta z. So our theta is gonna be from 0 to 2 pi. That we know. And we know that our radius is going to be from 0 to 1. Why? Because we want it within the cylinder. It's not within the sphere, it's within the cylinder. So then our radius is 1 because the radius of cylinder is 1, and that's where we solved it right here. Okay? And now our z, so this is what our z equals. This is basically the same equation of the sphere. So our boundaries from low to top is this and here, right? It's both the sphere. So this here is going to be negative rad 4. So it's going to be negative rad 4 minus r squared because it's on the lower. It's on the bottom of z equals 0. It's below of what z equals 0. So that means it's negative. It's negative z. So that's why it's negative, right? So then our top is just going to be the positive of that. So just 4 minus r squared because it's the top. It's the positive of z. Okay? Oops. My sweater is erasing. Alright, so now that we have this, we can now put it into our integral. So, I might erase this as well again. Just rewrite our integral. So it's going to be from 0 to 2 pi. From 0 to 1. Negative 4 minus r squared. Positive rad 4 minus r squared. And we don't have a function, as you can see. A function is not given. So that means there isn't a function for us to write here. So all we write is just r dz dr d theta. And then we integrate from that. So let me erase here. So we're going to use the small eraser. Okay, so we're going to move this to here. 0 to 1. R dz dr d theta. And then we can erase this. Okay, so now it's just solving this equation. So we first want to do it with respect to z. So we get from 0 to 2 pi. 0 to 1 gets z r, not z. Positive r squared dr d theta. So then that will be r times flat 4 r squared minus, but this is minus already, so then this is going to become positive r 4 minus r squared dr d theta. So now this is going to become just 2r times rad 4 minus r squared dr d theta. Alright, so if we let u equals 4 minus r squared, minus r squared, we get that u equals negative 2r dr. So let's hope we have enough space. So now that we're letting this u, let's first, before we get to this, let's separate these two because it's going to be much simpler. So let's first separate these. So now we're gonna move my error over here. So if we separate it, we're gonna have from 0 to 2 pi d theta, right? Times from 0 to 1, 2r. Okay, so this simply just becomes 2 pi. That's why we want to separate, so we can just get rid of this. We can get rid of this integral and d theta. So this becomes 2 pi. All right, so we have the answer to to part of the integral. So now let's do this. So we said that u equals 4 minus r squared. So we plug our u in here, so we get from 0 to 1, u to the half du. Okay, so integrating that. Remember, that's -2, so let's not forget the negative from here. So negative. So from there we get 2 over 3 integrating. So we get 3 over 2 from 0 to 1. So now when we plug back in our u, what our u equals, I always like to plug it back in. Three over 2 from 0 to 1. And so this becomes -2 over 3. When we plug in our limits, then we get the 3 to the rad 3 minus 8. And here we get -2 rad 3 plus 16 over 3. So when we multiply this with this, let me erase this part here. So when we multiply our two answers, pi times -3 plus 16 over 3, we get 32 pi over 3 minus 4 rad 3 pi. And that's our answer. So as you can see, the integration part, which we know already. We already know this part. The part is setting up our limits, knowing what the limits of the volume is, what they're asking for. That's the part, the tricky part that we first really need to emphasize on first, and figuring out, because the integration is the easy part. The integration is what we know already. All right. All right, so our third example is, it says, so of the triple integral of y times z dv, where e lies above the plane z equals 0, below the plane z equals y, and inside the cylinder x squared plus y squared equals 4. So let's draw our graph first. So it says the plane, above the plane, z equals 0. So above the plane, that means, like the first example that we did, that means it's going to be top here. It's not going to be the bottom. So we're not going to consider, so that means z is positive. It's always going to be positive. So we're not going to consider that part, all right? Then it says below the plane z equals y. Okay, so the plane z equals y, you can think of it as if it was y equals x, right? Y equals x is just basically a line like that, right? It's the same thing with z equals y. It's just basically a plane, a line. So the plane is going to be like that here. So it's going to be I'm a horrible drawer, so I'm very sorry. So like our plane is gonna be like that. This is our plane. It's gonna go like that. Okay? But we're gonna erase that so that we don't confuse, we don't mess up our graph. Okay, so that's our plane. Z equals Y. And then it says, and inside the cylinder, x squared plus y squared equals 4. So that means, you can tell already, from doing several examples, you're gonna notice, you can already see what your radius is gonna be. So that your radius is 2. So this right here, because it's below this plane and above z equals 0, so it's gonna be this part right here. It's kind of gonna look like this, like so. This is our plane, so it's gonna look like this. Let me erase our plane, so it's gonna look like this. So like cut out cylinder. Okay, so now that we have an idea of what we're integrating from, let's start doing our polar coordinates. Let's start converting, changing to polar coordinates. So we have that z equals y, right? So z equals y. Well, our y, changing it to polar coordinates, is simply just r sine theta. Okay, and then we do our cylinder, which is r squared equals 4, so r equals 4. As we previously have said, our radius would simply be 2. Okay, so now we get to do our limits. So let me make this smaller, it's too big. Alright, so z. So let's first start with the radius, because that's what we definitely know, right? So it's going to be from 0 to r to 2, okay? Now, our angle. If we look at this, our graph is only this part here. It's only half of it. We're not going this way like we have normally done in the previous examples. We're only doing this part right here, which is basically half of a cylinder. We're cutting it to be just the positive side because z equals 0, and then the plane is what makes it to just be this side right here. So that means we're not going all the way. We're not revolving in the whole circle. We're doing half of a circle. We're only doing this part, this side here. We're not considering this side. So that means if we're only doing half of the circle, then that means that our theta limits are 0 to pi, because we're doing only half. So our coordinates have to be from 0 to pi. Okay, so hopefully you can understand that we're only doing half. So that's why I previously have said from example 1 that it's always good to do your example, to do your graph, because you can understand it here. And if you're me, like visual learner, you have to actually draw something to be able to understand it and know what you're doing. So for you to be able to, if you're having difficulty just setting it up from this, draw it out. Doing your drawing, you're gonna notice, okay, this is only this part. So that is obviously a meaning. That's something different than from other problems where we have a cylinder where it's both sides here. It's only this side now. So it's gonna make you think, and you're gonna realize that it's now from 0 to pi. So having that, now our z is basically from 0 to our plane, and our plane is r. Remember, it's this, but we changed it to polar coordinates, so it's r sine theta. So it's from 0 to r sine theta. Okay, so now having our limits, we can now write our integral. From 0 to pi, from 0 to 2, 0 to r sine theta. And so we're given here a function, so we now have to convert that to polar coordinates as well. So our y is basically r sine theta times r dv dr d theta. Okay, so to get into our actual integrating this, I'm gonna erase here so we can have enough space. I'm gonna move this to here. So from 0 to pi, 0 to 2, and 0 to r sine theta. All right. So now we integrate in respect to z. We get from 0 to pi, 0 to 2, and z. Oh, I forgot the z. So be careful. So it's zr sine theta. Okay, so then our integration is 1/2 z squared r sine theta squared r squared. So from 0 to r sine theta dr d theta. Okay, so we plug that in. We get 1/2 r to the 4th power sine cubed dr d theta. Alright, so let's separate this so we can easily be able to solve it quickly. Not quickly, but more easier. So I'm gonna write 1 here. So I'm gonna do this one here, dr, and the other half here from 0 to pi sine cubed d theta. Okay, so this is simply 1/5 r to the 5th power from 0 to 2. And so our answer would be 16/5. Okay, so that's one of our answers. Now when we get to this, we can't directly integrate from there. So what we're gonna have to do is we're gonna have to split sine cubed and use our trig substitution. So when we split it, it would be sine theta, and so it would also then it would be sine squared theta, but we're gonna convert that to 1 minus cosine squared theta. And so if we let du equals sine theta, then our u has to be negative cosine. So when we plug in our u, get 1 minus u squared du. So integrating that, we get u minus 1/3 u to the cube from 0 to pi. We plug in back our cosine. So remember, our u equals negative cosine theta. So this is going to be negative cosine plus 1/3 times cosine cubed from 0 to pi. So when we plug in our limits, we end up getting 1 minus 1/3 minus -1 plus 1/3, which that is 2 minus 2/3, which equals 4/3. So there we have our two answers. So to have our full answer, we just multiply both of these together. So 16/5 times 4/3, we get 64/15. And that's our answer. Alright, so let's get to one more example that it's a bit different than these three examples that we've done. And okay, so our fourth example, I wanted to do something different. You may encounter something like this. So this is really similar to the first two examples we did, from changing from rectangular to cylindrical and cylindrical to rectangular. So this is similar, but now we're actually changing it in actual integral format. So as we first, like I said, we went over the whole coordinates thing. The key here is to do each separately and converting them separately to cylindrical coordinates. So if we start from here, so if we do this one first, so -2 to 2, meaning that it revolves a whole circle. So remember when we would do the picture, and the cylinder would be whole like this, right? So the radius would be 2, so that means this is 2, and this would be -2. So that means it revolves around. So our theta integral would be from 0 to 2 pi. So that's all it means. If it were to be from 0 to 2, so from 0 to 2, then that means it would only be half of a cylinder. So it would be from 0 to 2 pi. Like the previous example we did, the one we just did before, then that would be from 0 to pi. If it was from 0 to 2, then that would be 0 pi. But it's -2 to 2. So that's a whole circle, a whole cylinder. So it's from 0 to 2 pi. And if now we do this one right here. Alright, since it's a function of y, then we can write that x equals 4 minus y squared, since it's a function of y. Okay, and since we're dealing with dx and dy, then we can do this. We can write x equals square root of 4 minus y squared. So when we square both sides, we get x squared 4 minus y squared. You see what we're going at here? So this would be x squared plus y squared equals 4, which this is our r squared. So then our r just equals 2. So our integral of our radius of our r would be from 0 to 2. Okay? Now doing this right here. 2 is just a constant, so we can't do anything about that. There's no changing or there's no changing of pole coordinates we can do from there. So we know that our z integral, it's gonna be from this to 2, no matter what. But now this, look at this. X squared plus y squared, that's just r squared. So r squared, which just equals r. So then RZ integral would just be from r to 2. Okay. And then this, we just change that to polar coordinates like we've done in the other examples that we did. X is just r cosine theta, and z is z. There you go. And this right here is r dz dr d theta. All right, so now when we put all of these together, our integral is from 0 to 2 pi, from 0 to 2, r to 2, r squared cosine theta dc dr d theta. And this can easily be integrated. But this would be our answer. This is the integral of cylindrical coordinates from this. So this would be considered from the previous section, 15.7, the triple integral of in terms of f of x, y, and z. But this, you see how much simpler it is? The limits, they're so much easier than having to put this here and this here. I mean, when you do the integration of this, it's going to be so much more complicated than this. So thank God for cylindrical coordinates. All right, well, this is our end to this video. I hope you found it very helpful. It was a bit of difficulty for me the first 2 days that I learned of cylindrical coordinates, trying to figure out the limits. But like the advices I gave you is what helped me to understand every bit of it. And so I hope it helped you understand it as well.